Okay, so we just got done doing our cladding demo. We're going to go back to history. We have a little bit more to go on history here. In this 1960s, we had another individual work on the idea of Singlemode fiber. So up until now, kind of fiber was fiber. Now we have somebody working the idea, hey, there could be two different types of fiber. So introducing the idea of Singlemode fiber. Again, important, because as we look today, we have multi-mode, single-mode, different purposes, different uses. So if somebody coming on this scene trying to figure that out. Well, now we're also encountering a problem. With our glass, using glass as a means to send data, send a light signal, we start coming up with this problem. And I like this example. I had read this example in a book, so I like sharing this with you. Here's our problem. Think of an ordinary pane of glass like you have in a window in your house. If you take that pane of glass, just pretend it's maybe your sliding glass door in your dining room or window in your bedroom. If you go and get your Windex out and clean all the gunk off the inside, clean off all the gunk on the outside, all the bird poop and all that good stuff, clean all that gunk off, and you look through it, you might not even notice it's there. But if I take that pane of glass out of the window or out of the door and look at it from the edge, I now see that the glass looks green. This is kind of odd, but here's what's going on. If you think about looking through the window like you normally do, or your sliding glass door like you normally do, you're only looking through a pane of glass that's maybe 1/4 inch thick, maybe a little thicker if it's double pane and double glaze and all that good stuff. But it's really only 1/4 inch thick, 3/8 of an inch thick. It's not very thick, and because of that, it almost appears it's not there. But if I take that pane of glass out, or if I go to the hardware store and look at the glass rack where I can buy replacement glass to fix a window, and I look at that pane of glass from the edge. So, I'm now looking at it from the end. I'm looking at the little thin, the thin side, if you will. When I look through it, it appears green. Because I'm actually looking through a piece of glass now that might be 24 inches thick or 36 inches thick. And when I do that, it's now looking green because as the light is going through, it's bending. That pane of glass is acting almost like a prism and bending the light. So now think about, if I send light through a pane of glass like a normal window, and I send a flashlight through, it hardly gets affected. But if I try to, again, I spin that pane of glass and look at it from the edge and try to send the light through that pane of glass that's 36 inches thick, the light is not going to come out the other side as bright anymore because the glass is kind of bending that light or kind of using up the light, if you will, as it's going through. Well, now put that in perspective when you're talking about fiber optic. A piece of fiber optic that I'm sending light through is now a piece of glass that's 100 meters thick, 500 meters thick, 1,000 meters thick. So now imagine aiming a flashlight at a piece of glass that's 100 meters thick or 1,000 meters thick. How much light is getting through that piece of glass? That's the challenge. And we're talking, 1950s, 1960s, 1970s. The researchers working on this started realizing, whoa, as I start sending light through this piece of glass that's 100 meters thick or 1,000 meters thick, that glass is bending the light and not all of it's getting through. That's what makes fiber optics back, 50, 60 years ago a real challenge. So 1966, we have a very significant contribution. Charles Kao, and I apologize if I'm not pronouncing his name right, comes up with a report showing that optical fiber could carry data as long as the end-to-end signal loss is kept below 20 decibels per kilometer. This is important because we now have, I almost think of this as a hurdle or if you're a runner, you have hurdles that you're running over. He now set a bar or a hurdle that said, look, if we can make fiber optic good enough that we don't have loss that's 20 decibels per kilometer, if we keep our loss below that, 18 decibels, 15 decibels per kilometer, if we keep our loss below that, we can send data through fiber optic. That's important because we now have kind of a barrier or a hurdle that we can jump over to make this work. And actually, since that time, this is only a handful of years ago, 2009, he was awarded the Nobel Prize in Physics for this contribution, for figuring this out. He and his partner, Charles Hockham. These two were awarded the Nobel Prize in Physics for this contribution. Very huge. So if I put this number into scale for us, they figured out as long as the end-to-end signal loss is kept below 20 decibels per kilometer, well, 20 decibel loss would be about 99% loss. What they found out is if 1% of the light gets through our fiber, that's enough that a sensor could pick it up, and our signal is getting through that fiber. So if I shine a flashlight into a 1,000-meter piece of glass, 1,000-meter thick piece of glass, and 1% of the light gets through the other end, that glass is good enough to send data through. Woo! That's pretty cool. So now think about today and how we have hundreds to thousands of kilometer length piece of fiber optic. So in other words, we have glass that is 1,000 kilometers or 10,000 kilometers thick that we're getting light through. That's pretty impressive. So these guys figured out kind of the bar we need to hurdle over, and we started having scientists, research engineers coming up with ways to leap over that hurdle. And the next huge contribution came in 1970. A team by the name of Schultz Mauer and Keck, Peter Schultz, Robert Mauer, Donald Keck, came up with a way of producing fiber optic that is good enough, clean enough, that we can get that light through to transmit data. They figured out a way. They figured out the construction of the fiber and a way to make the fiber in such a way that is clean enough, good enough to get data through. And again, they have gone on to win all kinds of other awards, contributions to science and those sorts of things because of this work. And this came from Corning Glass, as in Corning Glass up in New York State, about 3 hours north of Harrisburg. They started figuring out a way to produce high-quality glass to beat this 20 decibel loss threshold, and they used a very unique method of doing it. I have a video later in our presentation. I'll talk about this later on how they did it, but very quickly, think of your solids, liquids, and gases. If I have a solid can hold lots of impurities. Think of a block of wood and driving a nail into it. That holds a pretty large impurity. If I have a liquid, think about your breakfast cereal and putting sugar in. I can scoop a couple, things of sugar in, and it'll dissolve into the milk. But if I keep scooping sugar in, eventually the liquid becomes supersaturated and all the sugar lays on the bottom of the bowl. So liquid can hold impurities, but not as much as a solid can. Well, how about a gas? How much impurities can a gas hold? Not much, because we're now down to the molecular level of ions, charged ions, if you will, hanging onto a molecule. That's about all a gas can hold as for an impurity. So they figured out a way to start making glass from a gas so they can control the impurity level to make a super clear glass. I will show you that a little bit later. I'll show you that process and even a video to show you that. But that's what they figured out. They can control the impurities in the glass because they were doing this from a gas. Pretty awesome stuff. Keeping going here, keeping going. They applied for a patent, 1970, patent number 3,711,262, basically getting the patent for this fiber and production of this fiber. They basically solved the problem that Dr. Kao presented or figured out. So Kao and the team of Mauer, Keck, and Schultz are significant in the production of fiber optic and the history of fiber optic. If you ever get a chance, quick little side note here. There is a museum up in Corning, New York. Again, that's only about 3 hours north of Harrisburg. It's not that far. Corning Museum of Glass. And there's all kinds of artwork and glass production and history of glass and everything else. And there's also kind of the industrial side where they actually have some displays about the history of fiber optic and these contributions. They have the Culloden experiment there. That's the Tyndall experiment. There's a jet of water where they're shooting blasts of light through it, and you can see the light go through the jet of water or the fountain of water. They also have a display showing how fiber optics produced. Again, I have a video on this a little bit later. They talk about the history of fiber optic, and in this display, if you zoom in on the corner up here, what you see is there's Mauer, Keck, and Schultz, and they talk about their contribution, including Charles Kayo's contribution to the production of fiber optic. Yeah, it's really if you're interested in the history of this, or the science of this, or the technical of this, it's a worthwhile thing to see when you get up there, if you get up there and go through the museum. I was up there, maybe about a year or so ago, so I took these pictures when I was up there. Yes, I'm that nerd. Here's a video describing a little bit about Corning Glass and their history, and it's actually some of the narrations done by Donald Keck. It's kind of interesting to watch. Some of it's a sales pitch, so to speak, for Corning, but it talks about their challenges in the production of glass to meet, fiber optic to meet the need. That'd be worthwhile watch if you have a couple minutes. 1975, government started linking all important computers, NORAD computers, using fiber optics. 77, telephone communication system installed, miles of fiber optic connecting, buildings and offices and COs and those sorts of things. And nowadays, today, we have fiber optic that is so pure that 10% of the light arrives at a receiver that's 50 kilometers away. And that's really 0.2 decibel meter of loss. So 60% of the light is actually transmitted over 10 kilometers. That's pretty awesome. Again, think of a 10 kilometer thick piece of glass where I could stand at one end and kind of wave to you and you'd be able to see me on the other end. That's pretty cool. And that's because of the techniques they figured out how to make this fiber optic so clear. Well, I'm going to stop there, and when we come back, I'm going to do another one on some of the general things about fiber optic that we want to remember.